There's something utterly humbling about staring up at the night sky, isn't there? A sea of stars stretching endlessly, each one a distant sun, each flicker a story we're only beginning to unravel. But beyond the familiar constellations and the glow of nearby planets, deep space holds secrets so bizarre, so utterly incomprehensible, that even the brightest minds on Earth are left scratching their heads. We're talking about phenomena that defy the laws of physics, cosmic oddities that make black holes look almost ordinary. And today, we're diving into 30 of the strangest, most baffling mysteries the universe has to offer, enigmas that challenge everything we think we know. Imagine a region of space where time itself seems to stutter, where galaxies behave as if they're being pulled by invisible hands, or where signals echo from the void with no discernible source. These aren't plot twists from a sci-fi novel, they're real, documented occurrences that scientists are still struggling to explain. Some of these phenomena hint at forces we've yet to discover, while others suggest that our understanding of reality might be missing entire chapters. And the deeper we look, the more questions we uncover, each one more tantalizing than the last. This journey isn't just about listing oddities, it's about stepping to the edge of human knowledge and peering into the unknown. Some of these cosmic puzzles might never be solved in our lifetime, and that's part of what makes them so thrilling. They remind us that the universe is far stranger, far more mysterious than we could have ever imagined. So, if you've ever looked up at the stars and wondered what's really out there, you're in the right place. Buckle up, we're about to explore the unexplainable. Deep in the cosmic shadows, hidden behind the thick dust and stars of our own Milky Way, lurks a gravitational mystery so powerful it's tugging entire galaxies off course. Scientists call it the Great Attractor, and it's one of the universe's most perplexing enigmas. Picture this: hundreds of galaxies, including our own, are being pulled toward a single point in space with unimaginable force, as if some invisible cosmic hand is reeling them in. The strangest part, we can't even see what's doing the pulling. This colossal anomaly sits in a region astronomers nicknamed the Zone of Avoidance, an area so crowded with interstellar gas and dust from the Milky Way's disk that optical telescopes struggle to peer through. It's like trying to spot a lighthouse through a blizzard. What little we've gleaned comes from X-ray and radio observations, which hint at a gravitational force equivalent to tens of thousands of Milky Ways combined. Yet despite its staggering influence, we still don't know if it's a single supermassive structure, a dense cluster of galaxies, or something even stranger like a flaw in our understanding of gravity itself. Some theories suggest the Great Attractor might be part of an even larger cosmic web, a knot in the fabric of space-time where dark matter and visible matter converge. Others propose it's just a temporary focal point in a much vaster flow, like a whirlpool in an intergalactic river. Whatever the truth, this invisible heavyweight reminds us how much of the universe remains hidden in plain sight, warping the paths of galaxies while keeping its secrets locked away behind a curtain of stars. The more we learn, the more questions arise. Why does its pull seem stronger than the visible matter we've detected? Could dark energy be playing a role? Every new observation peels back another layer of the mystery, proving that even in our own cosmic neighborhood, the universe still has tricks up its sleeve. If the Great Attractor shows us how much we still don't understand about gravity, then fast radio bursts are here to remind us that the cosmos has a flair for the dramatic. These bursts are like cosmic fireworks, blindingly bright flashes of radio waves that last just milliseconds, yet pack more energy than our sun emits in days. And they're not coming from nearby. These signals race across billions of light years, born in galaxies so distant their light is barely a whisper by the time it reaches us. What makes them truly baffling is their unpredictability. Some burst once and vanish without a trace, while others repeat in erratic patterns, like a Morse code operator with a broken key. One of the most famous, FRB 12-1859, has been caught erupting multiple times, sometimes in frantic clusters, other times with years of silence in between. It's as if the universe is teasing us, offering clues but refusing to follow a script. So what's causing these celestial fireworks? The leading suspect is Magnetar's highly magnetized neutron stars spinning so fast their magnetic fields snap like rubber bands, releasing colossal bursts of energy. But some bursts defy even this explanation, arriving with energies too extreme for known physics. Then there's the more speculative idea: could these be signs of alien technology? The notion isn't as far-fetched as it sounds. A civilization advanced enough to harness stellar energy might inadvertently produce signals detectable across the cosmos. Yet for every theory, there's a wrinkle. Some bursts arrive with a strange, sad trombone effect, their frequencies sliding downward as if the source is moving away at impossible speeds. Others are strangely clean, lacking the distortion expected from interstellar gas. Each new detection deepens the puzzle, proving that these fleeting signals are anything but simple. What's clear is that fast radio bursts are more than cosmic oddities, they're messengers. By studying how these waves twist and scatter as they travel, scientists are mapping the invisible matter between galaxies, piecing together the universe's hidden scaffolding. And who knows, one day these bursts might carry more than just static. They could be the key to unlocking secrets we haven't even thought to ask about yet. Just when we thought the Great Attractor was stretching the limits of our cosmic understanding, astronomers stumbled upon something even more unsettling: an inexplicable current sweeping entire galaxy clusters toward the unknown. They call it dark flow, and it's as if the universe itself is being tugged by a force we can't see, can't map, and can barely comprehend. Imagine dropping leaves into a river and watching them all drift inexplicably in the same direction, defying the current. That's what's happening to galaxies on the largest scales, moving with eerie synchrony toward a point beyond the edge of everything we can observe. This discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. Normally, this ancient light should be uniformly distributed, but researchers noticed subtle distortions, stretches where galaxy clusters appeared to drag this radiation along like footprints in wet sand. The implication: something massive, something beyond our cosmic horizon, is exerting a gravitational pull so immense it's altering the motion of entire superclusters. And that's where things get truly bizarre. According to our best cosmological models, the universe should be expanding evenly in all directions, with matter distributed randomly enough that no single region should dominate movement on such a colossal scale. Yet here we are, faced with evidence that thousands of galaxies are streaming toward a single point as if summoned. Some theories suggest this could be the gravitational echo of another universe beyond our own, a neighboring bubble in the multiverse yanking on ours like a magnet. Others argue it might be a flaw in our understanding of dark energy, or even a relic of the universe's birth, some primordial imbalance left over from the first fractions of a second after the Big Bang. But the most humbling possibility, that we're seeing the limits of our own perception. The observable universe is just a tiny fraction of what may exist, and dark flow hints at structures so vast, so alien, that they dwarf even the largest superclusters we've mapped. It's a reminder that for all our telescopes and supercomputers, we're still peering through a keyhole, trying to decipher a cosmos that refuses to fit neatly into our equations. Every time we think we've grasped the rules, the universe tosses another curveball, and dark flow might just be the strangest pitch yet. Amid the bustling cosmic neighborhoods where galaxies cluster like city lights, there exists a place so desolate, so shockingly empty, it defies everything we know about the universe's structure. Meet the Boötes Void, a spherical abyss spanning 330 million light-years, a region so vast you could fit thousands of Milky Ways inside with room to spare, yet it contains barely a handful of galaxies. It's not just a quiet corner of space, it's a cosmic desert, a void so profoundly empty that astronomers initially doubted their own instruments when they first mapped it in the 1980s. How does something this barren even exist? In a universe where matter clumps together under gravity, forming filaments and clusters like some grand cosmic web, the Boötes Void is a glaring anomaly. It's as if someone took a scoop out of the universe, leaving behind a bubble of near-nothingness. The few galaxies that do call this void home are isolated, drifting like lonely ships in an ocean of darkness. Some appear stretched and distorted, their light oddly red-shifted, as if the void itself is subtly reshaping them over eons. Theories about its origins range from the mundane to the mind-bending. One possibility is that smaller voids merged over billions of years, like soap bubbles coalescing into one gigantic hollow. Another suggests it's a remnant of the universe's infancy, a relic of primordial density fluctuations where matter simply never gathered. But the most tantalizing idea that the void isn't empty at all. It's filled with something we can't see. Dark energy, the mysterious force accelerating the universe's expansion, might dominate here, pushing matter away and leaving this eerie vacancy in its wake. What makes the Boötes Void truly unsettling is what it implies about the universe's structure. If such vast emptiness exists, could there be others? Astronomers have found smaller voids, but nothing on this scale. It challenges our assumption that matter is evenly distributed on the largest scales, hinting at a cosmos far lumpier and more unpredictable than we imagined. And if voids like this are more common than we think, they could rewrite our understanding of cosmic evolution, how galaxies form, how light travels, even how the universe might end. The Boötes Void isn't just a curiosity, it's a cosmic puzzle box. Every observation peels back another layer, revealing how little we truly grasp about the universe's grand design. It stands as a humbling reminder that even in the vastness of space, emptiness can be just as profound and just as mysterious as the brightest stars. Among the countless stars dotting our galaxy, one stands out not for its brilliance but for its baffling behavior. A star so unpredictable it has astronomers questioning everything they thought they knew about cosmic light patterns. Officially catalogued as KIC 8462852, but better known as Tabby's star, this distant sun in the constellation Cygnus flickers and dims in ways no ordinary star should, plunging by staggering amounts, up to 22% at times, as if something colossal is passing in front of it. And here's the kicker, whatever's causing these dips doesn't follow the rhythmic regularity of orbiting planets. It's erratic, almost chaotic, like a cosmic light switch being flicked by an unseen hand. When scientists first spotted these anomalies in data from NASA's Kepler Space Telescope, they expected a simple explanation, maybe a planet or even a debris field. But the numbers didn't add up. Even a Jupiter-sized world would only block about 1% of the star's light, and the dips were far deeper, lasting days or weeks with no discernible pattern. Some plunged sharply, others tapered gradually, as if the objects responsible were irregularly shaped or unevenly distributed. Theories exploded, ranging from the mundane to the extraordinary. Could a swarm of comets shattered by a nearby planet's gravity be casting these shadows, or was it something far stranger, like a colossal megastructure, an alien-built Dyson swarm designed to harvest the star's energy? The Dyson swarm hypothesis, while sensational, isn't pure science fiction. Imagine a civilization advanced enough to encircle its star with vast solar collectors, capturing its energy bit by bit. Such a structure would block light unevenly as it rotated, matching some of the star's bizarre dimming patterns. But before we declare evidence of extraterrestrial engineering, there are natural explanations still in play. Some suggest the star might be surrounded by dense clouds of interstellar dust, or perhaps it's recovering from a catastrophic collision that left it shrouded in debris. Others propose that Tabby's star itself is behaving abnormally, with internal processes we don't yet understand causing its light to stutter. Observations continue, with telescopes worldwide trained on this cosmic oddity. Recent studies reveal the star isn't just dimming erratically, it's also fading slowly over years, a phenomenon without clear precedent. Each new dataset adds layers to the mystery, ruling out some theories while giving others just enough credibility to keep hope alive. One thing's certain, Tabby's star is more than a curiosity. It's a beacon illuminating the gaps in our knowledge and reminding us that the universe has a penchant for defying expectations. Whether the answer lies in undiscovered physics, cosmic accidents, or something beyond our imagination, this star holds a lesson. Sometimes the most ordinary-seeming objects can hide the most extraordinary secrets. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, many likely hosting planets in the so-called Goldilocks zone, where conditions might be just right for life to emerge. Given those staggering odds, the cosmos should be teeming with civilizations, their signals crisscrossing the void, and yet when we listen, we hear only silence. This glaring contradiction is the heart of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If life is so probable, why does the universe seem so empty?" One chilling explanation is the Great Filter, a hypothetical barrier so immense it prevents life from advancing to the stage where it can colonize the stars. The terrifying part, we don't know if we've already passed this filter, like being the only species to evolve intelligence on Earth, or if it still lies ahead of us. Imagine a cosmic bottleneck, a challenge so deadly that almost no civilization survives it. It could be something as cataclysmic as self-destruction through war or environmental collapse, or perhaps a natural disaster we haven't even conceived of yet. The filter might explain why we see no signs of advanced life, because they've all hit a wall we haven't faced. Then there's the zoo hypothesis, the idea that extraterrestrial civilizations are out there but deliberately avoiding contact, observing us like animals in a cosmic nature preserve. It's a notion that blends awe with unease. Maybe they're waiting for us to reach a certain level of maturity, or perhaps they've set ethical boundaries against interfering with developing worlds. If true, it would mean we're part of a grand, invisible experiment, our planet a petri dish under the gaze of beings far beyond our comprehension. Other theories range from the practical to the bizarre. Maybe spacefaring civilizations are simply too far apart in time or distance to ever overlap. Or perhaps they've transcended physical forms, existing as digital intelligences in vast, hidden supercomputers, leaving no traces we'd recognize. There's even the dark forest hypothesis, a grim suggestion that every civilization stays silent because broadcasting your location invites destruction, like a hunter hiding in a forest where every rustle could be a threat. The Fermi paradox isn't just about aliens, it's a mirror held up to humanity. Are we alone because life is rare, or because intelligence is its own doom? Every search for extraterrestrial signals, every probe sent into the void, is an attempt to answer this profound question. Until we find proof, or until someone finds us, the silence of the universe remains one of its most unsettling mysteries. On the quiet night of August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a burst of radiation so powerful, so precisely tuned that the astronomer who discovered it scrawled, "Wow." In the margin of the printout, that single word gave the signal its name, and for 72 seconds, it blazed across the cosmos with an intensity unlike anything natural ever detected before or since. Tuned to the hydrogen line frequency, 1420 MHz, a band scientists had long theorized extraterrestrials might use for communication, the wow signal seemed almost too perfect. It was narrow, focused, and appeared to originate from the constellation Sagittarius, a region dense with stars, and then, just as suddenly as it arrived, it vanished. No echo, no repetition, no trace despite decades of searching. What made this signal so tantalizing wasn't just its strength or frequency, but its structure. Natural cosmic phenomena, pulsars, quasars, even the random noise of interstellar gas don't produce signals this clean. It wasn't a drift or a scatter of noise, it was a deliberate seeming spike, as if someone had aimed a cosmic flashlight directly at Earth. Astronomers ran through every possible explanation: a passing comet reflecting radio waves. No, none were in the area. A satellite or human-made interference. The telescope was designed to filter those out. Even now, over 4 decades later, no natural source has ever matched its profile. Theories about its origin range from the plausible to the extraordinary. Some suggest it could have been an intercepted burst from an alien beacon, perhaps a one-time transmission lost in the vastness of space. Others propose it was a rogue signal from a distant civilization's technology, a fleeting pulse we just happened to catch. Then there's the unsettling possibility that it was meant for us, but we missed the window to reply. If it came from a star system hundreds or thousands of light years away, any civilization that sent it might be long gone by now, their message a ghost in the cosmic ether. Efforts to relocate the signal have turned up nothing. The SETI Institute has scoured the same patch of sky with increasingly sensitive equipment, listening for even the faintest whisper of a repeat. Projects like Breakthrough Listen have expanded the search, scanning millions of frequencies across billions of stars. Yet the WOW signal remains stubbornly unique, a one-hit wonder in the universe's radio catalog. Its legacy endures because it represents the ultimate what-if. Of all the unexplained phenomena in astronomy, this one fits the mold of an intentional signal so closely that dismissing it feels premature. It's a reminder of how little we know and how much we might miss in the gaps between our observations. Maybe it was nothing more than a cosmic fluke, a quirk of physics we haven't yet unraveled. Or maybe, just maybe, it was the universe's way of testing whether we're truly listening. Either way, that scribbled "wow" still echoes through the decades, a silent challenge to keep searching. Picture the universe as a grand cosmic dance where galaxies whirl and stars pirouette in an intricate ballet. Now imagine that most of the dancers are invisible, their presence felt only by the way they pull on their visible partners. That's the essence of dark matter, the elusive substance that makes up 27% of the universe's mass energy content. We know it's there because without it, galaxies would fly apart, their stars scattering like beads from a broken necklace. The gravity required to hold them together far exceeds what visible matter can provide. Yet despite its overwhelming influence, dark matter refuses to show itself. It doesn't emit, absorb, or reflect light. It doesn't collide with ordinary atoms like billiard balls. It's a ghost in the cosmic machine, shaping the universe while remaining utterly unseen. So how do you hunt something that leaves no trace? Scientists have turned the cosmos into a detective's playground, searching for dark matter through ingenious and sometimes desperate methods. Some experiments, like those deep in abandoned mines or beneath mountains, rely on ultra-sensitive detectors waiting for the rare moment a dark matter particle might bump into an atomic nucleus. Imagine trying to catch a snowflake in a hurricane. That's the scale of the challenge. Others look for indirect clues: gamma rays streaming from galaxy cores where dark matter might annihilate, or subtle distortions in starlight as its gravity bends space like a lens. Even particle colliders like the Large Hadron Collider attempt to create dark matter in miniature cosmic crashes, smashing protons together at near light speeds in hopes of glimpsing something new. The leading candidate for dark matter's identity is the WIMP, weakly interacting massive particle. These hypothetical particles would be heavy, slow-moving, and barely interact with normal matter except through gravity. But after decades of searching, WIMP remains stubbornly hypothetical. This has led scientists to consider wilder possibilities: actions, particles so light they behave more like waves, or primordial black holes, relics from the universe's first second. Some theories even suggest dark matter isn't a particle at all, but a flaw in our understanding of gravity itself, a cosmic accounting error requiring new physics to balance the books. Every null result deepens the mystery. The more we fail to detect dark matter directly, the more it forces us to question fundamental assumptions. Could it be hiding in extra dimensions beyond our perception? Might it interact through forces we haven't discovered yet? The frustration is palpable, but so is the excitement. Dark matter isn't just a missing puzzle piece, it's a window into realms of physics we've barely begun to explore. And when, not if we finally unmask it, the revelation could rewrite the rules of reality as profoundly as quantum mechanics or relativity did. Until then, the hunt continues, a testament to science's greatest strength, the courage to chase shadows in pursuit of light. If dark matter is the invisible hand shaping the cosmos, then dark energy is the ghostly foot pressing on the accelerator, an enigmatic force not just stretching the universe, but doing so at an ever-increasing pace. Imagine blowing up a balloon with dots on its surface, watching them drift apart. But instead of slowing as the balloon expands, the dots suddenly start moving faster, as if the rubber itself were growing more elastic. That's the bewildering reality astronomers confirmed in the late 1990s when they measured distant supernova and found the universe's expansion wasn't just continuing, it was speeding up. This discovery flipped cosmology on its head. Until then, scientists assumed gravity would eventually slow the cosmic expansion, perhaps even reverse it in a big crunch. But dark energy, whatever it is, behaves like anti-gravity, pushing galaxies apart with a strength that grows as space itself expands. Unlike dark matter, which clumps and tugs, dark energy seems perfectly smooth, permeating every inch of the vacuum like an invisible mist with repulsive power. And here's the kicker, it makes up a staggering 68% of the universe's total energy content. That means the force we understand the least dominates everything we see. The leading theory pins dark energy on Einstein's cosmological constant, a term he once called his greatest blunder, which described empty space's innate energy. Quantum physics suggests that even a vacuum isn't truly empty. It's a seething foam of virtual particles flickering in and out of existence. These fleeting fluctuations could generate the repulsive pressure we observe. But there's a problem. Calculations predict a value trillions of times stronger than what we measure. This cosmological constant problem remains one of physics' greatest unsolved puzzles. Alternative ideas abound. Some propose dark energy isn't constant at all but a dynamic field, like an evolving fifth force of nature. Others suggest our understanding of gravity breaks down on cosmic scales, requiring a rewrite of Einstein's equations. Then there's the spine-chilling possibility that dark energy's strength could change over time, potentially tearing atoms apart in a big rip billions of years from now. What makes dark energy so unnerving is its existential weight. It doesn't just shape the universe's fate, it hints at gaps in our knowledge deeper than we imagined. Every galaxy, every star, every atom is caught in its tide, racing toward a future where distant lights will blink out one by one, their signals stretched beyond detectability. It's a humbling reminder, we're not just decoding the universe's secrets, we're witnessing its endgame in real time. High above Earth, lost in the sea of modern satellites and space junk, lurks one of the most persistent cosmic conspiracy theories of all time, the Black Knight. Stories swirl about this enigmatic object, an ancient alien probe silently circling our planet for millennia, watching, waiting. Some claim it predates human spaceflight by thousands of years, a relic of an advanced civilization that visited long before pyramids or Stonehenge. Others insist it's been broadcasting signals since the late 19th century, when Nikola Tesla reportedly intercepted strange radio pulses he believed originated from beyond Earth. But what's really up there? The myth took root in 1954 when newspapers reported the U.S. Air Force had detected two unidentified satellites orbiting Earth, impossible at the time, since no nation had yet launched one. Sensationalists seized on this, weaving tales of extraterrestrial surveillance. The legend grew with grainy photos from NASA missions in the 90s, showing dark, irregular shapes near the shuttle, which believers dubbed the Black Knight. The most infamous image, a 1998 Endeavour mission photo of what was clearly a thermal blanket lost during a spacewalk, but conspiracists declared it proof of an otherworldly spacecraft. Here's where reality intrudes. Astronomers and debunkers have identified the most likely candidates for Black Knight sightings, chunks of space debris like discarded rocket fairings or defunct satellites, tumbling in erratic orbits that can look sinister through a lens of paranoia. They're anomalous radio signals, often natural pulsars or terrestrial interference misinterpreted by overeager listeners. Even Tesla's famed interception lines up with known phenomena like plasma oscillations in Earth's ionosphere. Yet the allure persists. Part of what makes the Black Knight so captivating is its role as a Rorschach test for our cosmic anxieties. In an age where governments deploy spy satellites and corporations dominate low Earth orbit, the idea of something older, something not ours watching from the darkness taps into primal fears. Could there still be a kernel of truth hiding in the noise? Modern sky surveys and radar tracking have catalogued nearly every sizable object orbiting Earth, and none match the descriptions of a 12,000-year-old alien artifact. But in the vastness of space, where a single piece of debris can vanish for decades only to reappear unexpectedly, the Black Knight's legend thrives on the gaps in our knowledge. Perhaps the real mystery isn't whether an alien satellite exists, but why we're so eager to believe it does. The Black Knight reflects humanity's timeless hunger for hidden narratives, for proof that we're not alone in the universe, even if that proof is just a lost piece of thermal blanket drifting silently through the void. The cosmos is not a peaceful place. While galaxies might look serene and unchanging from our vantage point, they are locked in an endless dance of destruction and rebirth where the strong consume the weak in a process as ancient as the universe itself. This is galactic cannibalism, the violent, beautiful act where larger galaxies tear apart and absorb smaller ones, reshaping themselves in the process. And far from being rare, it's one of the most fundamental ways galaxies grow. Take our own Milky Way, seemingly stable, but already a product of countless mergers. Astronomers have identified the shredded remains of at least a dozen smaller galaxies it has devoured over billions of years, their stars now strewn through our halo like cosmic crumbs. The most recent victim, Gaia Enceladus, was a dwarf galaxy nearly a quarter our size, torn apart and digested in a cataclysm that shook the Milky Way 8 to 10 billion years ago. Even now, we're in the act of consuming the Sagittarius dwarf spheroidal, a tiny satellite galaxy whose stars are being siphoned away in long, shimmering streams visible in telescope surveys as ghostly tendrils wrapping around our galactic disk. But the most dramatic example lies just 2.5 million light-years away. Andromeda, our colossal neighbor, itself a product of past mergers. Hubble's Space Telescope images reveal its halo littered with the remnants of devoured galaxies, and here's the twist: it's on a collision course with us. In about 4 billion years, the Milky Way and Andromeda will slam together in a slow-motion crash lasting hundreds of millions of years. Stars, too spaced out to collide, will instead be flung into wild new orbits, while vast clouds of gas compress, igniting bursts of new star formation. The end result, a single, monstrous elliptical galaxy nicknamed Milkdromeda, a hybrid titan bearing little resemblance to the elegant spirals we know today. What makes galactic cannibalism so mesmerizing is the sheer scale of violence wrapped in silent elegance. Hubble's snapshots of other merging galaxies, like the Antennae galaxies or the Mice, show the process in action: twin cores swirling closer, their spiral arms stretched into long, luminous tidal tails studded with newborn stars. These collisions aren't just destructive, they're creative. The chaos compresses gas clouds, triggering stellar nurseries where none existed before. Supermassive black holes at their centers, once dormant, awaken to feast on infalling matter, blazing as quasars visible across the universe. Yet for all their fury, these mergers unfold with a strange grace. Gravity weaves the devoured galaxies, stars into intricate shells and streams, patterns so precise they allow astronomers to reconstruct the victim's original size and trajectory billions of years later. It's forensic astronomy reading the scars of ancient collisions to piece together a galaxy's violent past. And this isn't some distant phenomenon, it's our fate. Every galaxy we see, no matter how majestic, is either a predator, a survivor, or like our own, both. The universe, it seems, runs on a simple rule: grow or be eaten. In the vast emptiness between planets, where the laws of physics should be as predictable as clockwork, NASA Pioneer probes did something inexplicable. They started slowing down. Launched in the early 1970s, Pioneer 10 and 11 were trailblazers, the first human-made objects to venture beyond the asteroid belt, fly past Jupiter and Saturn, and eventually leave the solar system entirely. But as they sped toward interstellar space, mission controllers noticed something odd. Their deceleration didn't match the expected trajectory. It was as if an invisible hand was gently but persistently tugging them backward. This discrepancy, known as the Pioneer anomaly, became one of spaceflight's most stubborn mysteries. The probes were slowing at a rate of about 300 nanometers per second, squared, a fraction so tiny it sounds negligible, but over decades and billions of miles, it added up to thousands of miles off course. At first, scientists scrambled to find exotic explanations. Could it be the gravitational pull of undiscovered dark matter, a flaw in our understanding of Einstein's general relativity? Or something even stranger, like the influence of unseen dimensions? The truth turned out to be far more mundane, yet no less fascinating. After years of painstaking analysis, researchers discovered the culprit wasn't lurking in the shadows of deep space, it was baked into the probes themselves. Pioneer's design included nuclear-powered heat sources called RTGs, which generated electricity by converting the decay of plutonium into warmth. That heat didn't just power the spacecraft, it radiated outward unevenly. The front of the probes, with their dish-shaped antennas, acted like reflectors, bouncing thermal radiation backward. Each tiny photon emitted carried a minuscule amount of momentum, enough, when multiplied by trillions upon trillions of emissions over decades, to create the illusion of a mysterious drag force. This revelation was a masterclass in scientific humility. What seemed like a cosmic anomaly was actually a lesson in engineering subtleties. The Pioneer anomaly reminds us that even in the cold precision of space, the devil's in the details, sometimes literally. Thermal radiation, a force so slight we rarely notice it on Earth, became the hidden variable rewriting the story of these iconic missions. And while the mystery is now solved, its legacy endures, proving that the universe's greatest puzzles aren't always found in distant galaxies. Sometimes they're hiding in plain sight, radiating gently from the spacecraft we built ourselves. On October 19, 2017, astronomers spotted something that shouldn't have been there. A tiny, faint object streaking through our solar system at blistering speeds, its trajectory so extreme it could only have come from interstellar space. They named it Oumuamua, Hawaiian for scout or messenger from afar, and for the brief window it was visible, this cosmic visitor sparked a firestorm of debate. Here was the first confirmed object from another star system passing through our cosmic neighborhood, but the closer scientists looked, the stranger it became. First, there was its shape. Most asteroids and comets are roughly spherical or lumpy, but Oumuamua defied expectations. Based on the way its brightness fluctuated, it appeared to be tumbling end over end like a thrown stick, suggesting an elongated form at least 5 to 10 times longer than it was wide. Some calculations even hinted at a pancake-like flatness, unlike anything seen in our solar system. Then came the real puzzle, its acceleration. As it hurtled away from the sun, instead of slowing predictably under gravity's pull, Oumuamua sped up slightly, as if nudged by an unseen force. Comets often exhibit similar behavior when their ices vaporize, creating a gaseous jet, but Oumuamua showed no visible tail, no coma, no outgassing at all. Cue the theories, some grounded, others wildly speculative. Harvard astronomer Avi Loeb famously suggested Oumuamua could be artificial, perhaps a light sail, a thin, reflective structure pushed by starlight, akin to humanity's own experimental solar sails. Its flat shape and unexplained acceleration fit, he argued, raising the tantalizing possibility it was a derelict probe or even an intentional artifact. Others countered with natural explanations. Maybe it was a hydrogen iceberg sublimating invisibly in sunlight, or a fractal-like dust aggregate so porous it reacted to solar radiation like a cosmic kite. The truth we may never know. By the time Oumuamua was detected, it was already speeding away, too distant for follow-up observations. What lingers isn't just the mystery of Oumuamua's identity, but what it represents. Interstellar objects likely pepper our solar system unnoticed, their visits brief and unannounced. Some could be fragments of distant exoplanets shattered in collisions, others, icy nomads flung from their home systems by gravitational chaos. Each one carries clues about how planetary systems form and evolve beyond our own, if we're quick enough to catch them. Future telescopes like the Vera Rubin Observatory promise to spot more of these visitors, perhaps even before they swing past the sun. Until then, Oumuamua remains a cosmic Rorschach test, a glimpse into the unknown, revealing as much about our imagination as it does about the universe's secrets. What if everything we thought we knew about the universe's birth was subtly wrong, not because the data is flawed, but because the cosmos itself is playing tricks on us? That's the unsettling question raised by the so-called axis of evil, a pattern in the cosmic microwave background that seems to align eerily with the plane of our solar system. The CMB is the oldest light in the universe, a fossilized glow from the Big Bang's afterglow, and it should be uniformly random like static on an old TV. But when scientists mapped its tiny temperature fluctuations, they found something bizarre. Certain large-scale patterns weren't scattered randomly. They appeared oddly aligned with our solar system's orientation, as if the universe had quietly drawn a bullseye around us. This discovery throws a wrench into one of cosmology's bedrock principles, the Copernican idea that Earth holds no special place in the universe. The alignment, dubbed the axis of evil half-jokingly by researchers, shouldn't exist. Inflation theory predicts the CMB's fluctuations should be isotropic, meaning no direction is privileged over another. Yet here we are, with anomalies that seem to whisper we might be, against all odds, somehow central to the universe's structure. The implications are staggering. Could this be evidence of undiscovered physics, a flaw in our models, or more unsettlingly, a sign that the universe has a fundamental preferred direction? Some physicists argue it's just a statistical fluke, a cosmic mirage born from the way we process CMB data. Others propose wilder explanations. Perhaps our universe collided with another bubble universe in the multiverse, leaving a scar in the CMB. There's even the radical suggestion that pre-Big Bang relics, structures from a prior cosmic cycle, imprinted this pattern, but the most haunting possibility, that we're seeing the limits of human perception. The CMB is like a photograph taken through a foggy lens. Maybe what we call anomalies are just artifacts of how we're forced to observe the cosmos from our tiny vantage point. The axis of evil remains unresolved, a thorn in the side of modern cosmology. It challenges not just our models, but our philosophical assumptions about randomness and our place in the grand scheme. Until we crack its code, it stands as a humbling reminder. The universe might not just be stranger than we imagine, but stranger than we can imagine. In the grand tapestry of the cosmos, where galaxy clusters weave delicate filaments across unfathomable distances, one structure stands out not just for its scale, but for the way it shatters our understanding of what's possible. Meet the Hercules Corona Borealis Great Wall, a mind-bending conglomeration of galaxies stretching an astonishing 10 billion light-years across. To put that in perspective, it's so vast that if you could travel at the speed of light, it would take you twice the age of Earth just to go from one end to the other. This isn't just a cosmic landmark, it's a paradox wrapped in starlight, defying everything we thought we knew about the universe's early architecture. What makes this galactic megastructure so baffling isn't just its size, it's its age. Based on our current models of cosmic evolution, the universe simply hadn't existed long enough after the Big Bang for gravity to sculpt something this enormous. The Great Wall emerged when the cosmos was barely 3 to 4 billion years old, a cosmic toddler by universal standards. Picture building a skyscraper the height of Mount Everest in a single afternoon. That's the scale of this anomaly. How could gravity, limited by the speed of light, have orchestrated such a sprawling assembly of matter in such a short time? Theories abound, each more daring than the last. Some suggest this wall isn't a single structure but a chance alignment of multiple filaments, like shadows overlapping on a cave wall. Others propose exotic physics at play. Perhaps dark energy behaved differently in the early universe, accelerating matter clustering in ways we can't yet replicate in simulations. Then there's the radical idea that the Great Wall hints at primordial irregularities in the fabric of spacetime itself, wrinkles left over from the universe's birth that acted as blueprints for later structure. Adding to the mystery is its ghostly composition. Mapping the Hercules Corona Borealis Great Wall is like trying to trace the outline of a city using only flickering candles. Most of its mass is invisible dark matter, with galaxies merely marking its densest knots. Yet even these visible traceries defy expectations, arranged in a grid-like pattern that resembles a cosmic honeycomb. Some astronomers argue this could mean we're seeing not just one wall, but an intersection of multiple superstructures, a crossroads in the universe's large-scale web where filaments entwine. The implications ripple far beyond cosmology textbooks. If structures this massive existed so early, our simulations of cosmic evolution might be missing fundamental ingredients. Could there be unknown forces acting on dark matter? Was the early universe more dynamic, more chaotic than we've assumed? Every new observation peels back another layer, revealing how little we truly grasp about the universe's adolescence. The Hercules Corona Borealis Great Wall isn't just a curiosity, it's a challenge, a cosmic dare urging us to rethink the very foundations of how we model spacetime's grand design. At first glance, the Red Rectangle Nebula seems like something out of a cosmic geometry textbook, a glowing, symmetrical structure floating in the void, its sharp angles and vivid hues defying the usual chaotic beauty of deep space. Located about 2,300 light-years away in the constellation Monoceros, this striking nebula earned its name not just from its shape, but from the deep crimson glow that bathes its intricate lattice of beams and crossbars. But what makes this celestial object truly extraordinary isn't just its appearance, it's the bizarre chemistry unfolding within it, a puzzle that's reshaping how we understand the final acts of dying stars. Most planetary nebulae, glowing shells of gas ejected by aging stars, are messy, asymmetrical affairs, their structures sculpted by chaotic stellar winds. The Red Rectangle is different. At its heart lies a binary star system, HD 44179, where one star has already shed its outer layers, while its companion stirs the expelled material into an almost unnatural order. The result, a vast X-shaped framework of dust and gas, illuminated by the dying star's ultraviolet light, with concentric rings that resemble rungs on a ladder. This precision is so rare that astronomers initially suspected imaging artifacts until closer inspection revealed nature had crafted a near-perfect lattice. Yet the real mystery lies in the nebula's chemistry. Unlike most nebulae which glow from familiar elements like hydrogen and helium, the red rectangle emits strange infrared signatures linked to complex organic molecules called polycyclic aromatic hydrocarbons, PAHs for short. These carbon-rich compounds, often found in soot or engine exhaust on Earth, shouldn't survive the harsh radiation of a stellar death throes. Their presence here suggests a cosmic alchemy we're only beginning to decode. Even more intriguing are the unexplained red emission bands, ghostly spectral lines that no known molecule on Earth can account for. Some researchers speculate these could be from entirely new forms of carbon-based matter, forged in conditions impossible to replicate in labs. What makes the red rectangle so invaluable is its role as a cosmic time capsule. It captures a fleeting phase in stellar evolution, the moment a sun-like star transitions into a white dwarf, seeding space with the raw ingredients for future planets and perhaps even life. The symmetrical outflows suggest binary stars might sculpt planetary nebulae into shapes we've barely begun to catalogue, while the organic molecules hint at how the building blocks of life could scatter across galaxies. Future telescopes like the James Webb Space Telescope aim to study its chemistry in unprecedented detail, potentially unlocking secrets about how complex molecules survive and thrive in the hostile environments around dying stars. The Red Rectangle Nebula is more than a curiosity. It's a window into the universe's hidden artistry. Its geometric perfection challenges our assumptions about chaos in stellar deaths, while its chemical mysteries remind us how much we have yet to learn about the interstellar ingredients that might one day form new worlds. In its crimson glow, we see not just the end of a star, but the promise of cosmic rebirth. Imagine a world where the ground beneath your feet isn't rock or sand, but solid diamond. A planet so dense with crystallized carbon that its entire mass could be one colossal gemstone. That's not science fiction, it's the reality of PSRJ 1719-1438b, a planet orbiting a pulsar 1,200 light-years away in the constellation Serpens. This exotic world, no larger than Jupiter but packing far more mass, likely began its life as a star. But after its companion went supernova, the dying star's outer layers were stripped away, leaving behind a corpse so dense its carbon core crystallized under unimaginable pressure. The result, a planet that might be, quite literally, a diamond the size of a solar system. What makes this cosmic jewel so fascinating isn't just its composition, it's the brutal conditions that forged it. The pulsar it orbits, a rapidly spinning neutron star, bathes the planet in intense radiation while gravitational forces squeeze its carbon into a crystalline lattice. Earth, by contrast, is a rocky world rich in oxygen and silicon, with carbon making up just a fraction of a percent of its mass. But on PSRJ 1719-1438b, carbon could account for most of the planet's volume, compressed into forms we've only created in labs for fleeting moments. If you could stand on its surface, an impossible feat given the crushing gravity and lethal environment, you might be walking on a crust of diamond hundreds of miles thick, with even deeper layers compressed into stranger phases like liquid metallic carbon. Yet for all its glamour, this diamond planet is a monument to cosmic destruction. Its existence hints at a violent past where two stars once danced in a binary system, until one exploded and the other was reduced to a glittering relic. The pulsar's gravity now whips the planet around in a 2-hour orbit, so close that stellar winds blast its surface relentlessly. It's a far cry from Earth's gentle dance with the sun, where liquid water and organic chemistry thrive. Could such a world ever harbor life? Almost certainly not, but it does raise tantalizing questions about the diversity of planetary formation. If diamonds can crystallize on this scale, what other exotic states of matter might exist in the universe? And if carbon, the backbone of life here, can dominate entire worlds elsewhere, does that mean Earth's chemistry is just one possibility among many? PSRJ 1719-1438b offers no easy answers, only a glittering reminder that the cosmos is far stranger and far more creative than we ever imagined. The universe operates on a simple rule: information, like energy, can never truly be destroyed, only transformed. Flip a coin, burn a book, or shatter a vase, and in theory, you could work backward from the remains to reconstruct the original. But throw something into a black hole, and this fundamental law seems to break down spectacularly. That's the heart of the black hole information paradox, a puzzle so profound it made Stephen Hawking famously bet against his own theory and lose. Hawking's work in the 1970s revealed that black holes aren't entirely black. They emit faint radiation, now called Hawking radiation, slowly evaporating over eons. But here's the catch: this radiation appears random, carrying no trace of the matter that fell in. A book, a star, or an entire civilization, once swallowed, their unique information would vanish into a featureless hum of particles. That violates quantum mechanics, which insists information must always be preserved. The paradox pits general relativity against quantum theory in a showdown that's baffled physicists for decades. Recent breakthroughs, however, suggest a resolution might lie in the bizarre world of quantum gravity. One leading idea is the holographic principle, which posits that all the information falling into a black hole isn't lost, it's encoded on its event horizon, the point of no return. Think of it like a cosmic scratchpad. As matter crosses the threshold, its data gets smeared across the surface in quantum bits, later echoed outward in Hawking radiation. Imagine dipping your hand into a pond. The ripples carry a distorted but complete record of the intrusion. Similarly, black holes might remember by etching information onto their boundaries, preserving it even as the interior becomes an inscrutable void. Even stranger is the concept of quantum entanglement's role. When particles escape as Hawking radiation, they're entangled with the black hole's interior. Over time, this creates a dense web of connections, forming what's called a quantum wormhole or Einstein-Rosen bridge. These aren't tunnels through space, but intricate correlations in the radiation itself, threads that might stitch the lost information back into the universe. In 2019, a landmark calculation showed that under strict quantum conditions, information could indeed escape, resolving Hawking's paradox mathematically. Yet mysteries linger. If information escapes, where does it go? Is it scrambled beyond recognition, like a burned letter whose ashes still hold the words if you know how to look? Or does it re-emerge intact, waiting to be decoded? The answer could redefine our understanding of spacetime itself, revealing it as a dynamic, holographic fabric where nothing is ever truly lost, only hidden in plain sight. The black hole information paradox isn't just about collapsed stars. It's a gateway to the universe's deepest operating system, and we're finally starting to crack the code. Beyond the orbit of Neptune, where sunlight is just a faint glimmer, lies a cosmic junkyard of frozen leftovers from the solar system's birth, the Kuiper Belt. This vast donut-shaped region is packed with icy worlds like Pluto, Haumea, and Makemake, along with countless smaller objects tumbling through the darkness. But something peculiar happens when astronomers map the belt's outer edges. Instead of a gradual thinning of debris, they hit a wall, a sudden, inexplicable drop in objects so sharp it's been dubbed the Kuiper Cliff. It's as if someone drew a line in the cosmic sand and declared, nothing beyond this point. This abrupt boundary sits roughly 4.8 billion miles from the Sun, where the number of Kuiper Belt objects plunges by almost 90%. That kind of steep cutoff isn't just unusual, it defies everything we know about how planetary systems form. The outer solar system should resemble a smooth gradient, with debris fading slowly into the Oort cloud. The cliff suggests something intervened, either an unseen force still at work today or a cataclysmic event frozen in time. One leading theory points to an undiscovered planet lurking in the shadows. Dubbed Planet 9 by researchers, this hypothetical world could be 10 times Earth's mass, orbiting far beyond the cliff's edge. Its gravity might act like a cosmic plow, scattering or hoarding smaller objects into unnatural clusters. Computer simulations show such a planet could carve gaps like the Kuiper Cliff while also explaining the bizarre, tilted orbits of some distant objects. Yet despite years of searching, no telescope has spotted this phantom world, leaving astronomers to wonder if it's real or just a mathematical ghost. Then there's the possibility of a violent past. Early in the solar system's history, a close encounter with a passing star could have ripped away the outer Kuiper belt like a tidal wave stripping a beach. Or perhaps Neptune's migration, when it drifted outward billions of years ago, triggered gravitational chaos, flinging objects into deep space or the sun. Even the faint pull of the Milky Way's tides might have played a role, slowly eroding the belt's outer fringe over eons. The Kuiper Cliff isn't just a curiosity, it's a detective story written in ice and rock. Every new survey of the distant solar system, like the Vera Rubin Observatory's upcoming census, could bring us closer to cracking the case. Until then, this silent boundary stands as a reminder that even in our own cosmic backyard, the universe keeps its most guarded secrets just out of reach. Hidden within the faint glow of the cosmic microwave background, the afterglow of the Big Bang, lies a chilling anomaly, the Eridanus supervoid, a vast emptiness so immense it's been dubbed the universe's cold spot. Stretching an astonishing 1.8 billion light-years across, this region is noticeably colder than its surroundings, as if some cosmic hand had scooped out a chunk of the universe and left behind a frigid shadow. But what could possibly create such a void, and why does it defy our expectations of how matter and energy should be distributed? At first glance, the cold spot seems like a simple absence, a place where galaxies and galaxy clusters are unusually sparse. In a universe where matter clumps together under gravity, voids aren't entirely unexpected, but the Eridanus supervoid isn't just any empty patch. It's so colossal that, according to standard cosmology, it shouldn't exist at all. The temperature dip in the cosmic microwave background suggests this void isn't merely a gap. It's an active drain on energy. Photons traveling through it lose a tiny fraction of their energy as they cross, a phenomenon called the integrated Sachs-Wolf effect. The problem: the void's size and depth can't fully account for the temperature drop. There's something else at work here, something unexplained. This discrepancy has led to some wild theories. One provocative idea is that the cold spot might be evidence of a collision with another universe, a bruise left by a cosmic encounter in the multiverse. In this scenario, our universe could be one bubble among many, and the Eridanus supervoid might mark where another bubble briefly brushed against ours, siphoning away energy and leaving behind an unnatural chill. It's a staggering thought, the cold spot as a cosmic fingerprint, proof we're not alone in the greater multiverse. Yet not all scientists are ready to embrace such exotic explanations. Some argue the cold spot could be a statistical fluke, an unlikely but not impossible quirk in the cosmic microwave background. Others suggest it might be the imprint of a primordial defect in spacetime, a relic from the universe's earliest moments when the fabric of reality was still settling into place. There's even the possibility that dark energy, the mysterious force accelerating the universe's expansion, behaves differently in voids, amplifying their cooling effect. The truth remains elusive, but the Eridanus supervoid continues to captivate astronomers precisely because it resists easy answers. Whether it's a window into parallel universes, a relic of cosmic defects, or simply a fluke of nature, this icy expanse challenges our understanding of the universe's structure and evolution. Every new observation, from galaxy surveys to refined CMB measurements, peels back another layer of the mystery, and until we solve it, the cold spot stands as a humbling reminder. Even in the vast, well-mapped cosmos, there are still regions so strange they defy explanation. In the vast radio silence of space, astronomers recently stumbled upon something utterly perplexing: massive, ghostly rings glowing in radio waves, so enormous they could swallow entire galaxies. These odd radio circles, or ORC, weren't predicted by any model, and they've left scientists scrambling for explanations. Imagine looking up at the night sky and spotting a perfect, faint ring the size of the full moon, except this ring isn't optical. It's invisible to the naked eye, detectable only by radio telescopes. Even stranger, these structures don't seem to correspond to anything visible in other wavelengths. No stars, no galaxies, no obvious source, just eerie, symmetrical halos hanging in the void like cosmic smoke rings. The discovery came in 2020 when researchers analyzing data from the Australian Square Kilometre Array Pathfinder noticed these strange formations. Each ORC spans hundreds of thousands of light years, far larger than any known supernova remnant or galactic outflow. At first, astronomers suspected instrument glitches or artifacts, but follow-up observations with other telescopes confirmed their reality. Now, theories about their origins range from the explosive to the downright exotic. One leading idea ties them to galactic winds, colossal outflows of gas and particles unleashed by starburst galaxies where stars form at frenetic rates. These winds could collide with intergalactic gas, creating shock waves that emit radio emissions in perfect rings. Yet ORCs appear isolated, with no obvious galaxy at their center to drive such outflows, leaving this explanation on shaky ground. Then there's the more speculative angle. Could these rings be the fingerprints of something even stranger, like wormholes or failed black hole mergers? Some theorists suggest ORCs might trace the edges of spacetime tunnels, their radio glow coming from particles accelerated at the mouths of these hypothetical passageways. Others propose they're the aftermath of gargantuan black hole eruptions, where jets punch through intergalactic gas, leaving behind circular ripples like stones dropped in a pond. The most tantalizing possibility, that ORCs represent an entirely new class of astrophysical phenomenon, something we've never before encountered or even imagined. What makes ORCs so captivating isn't just their mystery, but what they reveal about the limits of our cosmic maps. Radio astronomy has long uncovered hidden structures, quasars, pulsars, even the cosmic microwave background, but ORCs remind us that the universe still holds surprises in plain sight. Future telescopes like the Full Square Kilometre Array may soon peer deeper into these enigmatic rings, decoding their origins. Until then, they stand as silent sentinels, challenging us to rethink what we know about the invisible forces shaping the cosmos. Most planetary systems follow an elegant, almost clockwork logic. Planets orbit their stars in neat, aligned planes, like pearls strung along a cosmic wire. But then there's KOI-5ab, a renegade world that seems to revel in chaos. This gas giant, roughly half the mass of Saturn, doesn't just orbit one star, it's part of a triple star system where gravitational forces twist and pull in every direction. And if that weren't turbulent enough, KOI-5ab's orbit is wildly misaligned, tilted a staggering 50 degrees relative to the plane of its stellar trio. It's as if someone tossed a planet into a celestial mosh pit and let the stars kick it into a path defying all expectations. The KOI-5 system, located about 1,800 light-years away in the constellation Cygnus, is a cosmic circus. At its heart, two stars, KOI-5a and KOI-5b, dance in a tight 30-year orbit, while a third star, KOI-5c, circles them both every 400 years. Normally, planets in multi-star systems align with the primary star's orbital plane, like a well-behaved extension of the system's architecture. But KOI-5ab bucks the trend, looping around KOI-5a at a severe angle, as if it were flung into orbit by some ancient gravitational slingshot. How does a planet even form in such a gravitational maelstrom? The leading theory suggests KOI-5ab might be a survivor of a far messier past. In its infancy, the protoplanetary disk, the swirling ring of gas and dust where planets are born, could have been yanked and warped by the competing pulls of the three stars. Imagine trying to lay a flat sheet on a bed while three people tug it in different directions. The material bunches and twists unpredictably. Alternatively, KY5AB might have started life in a more conventional orbit, only to be knocked askew by a close encounter with another massive object, perhaps a rogue planet or a passing star. What makes this misaligned world so fascinating isn't just its defiance of norms, it's what it reveals about the resilience of planetary formation. Even in the most chaotic environments where gravitational forces rage like storm winds, planets can still emerge. KY5AB forces us to reconsider how adaptable nature can be, crafting worlds in conditions we once thought too hostile. Future observations, especially with telescopes like JWST, could unveil more about its atmosphere and composition, offering clues to its turbulent origins. For now, this cosmic oddball stands as a reminder. The universe doesn't play by our rules. It writes its own, often in the most spectacularly crooked lines. We've mapped galaxies, weighed black holes, and even calculated the invisible grip of dark matter, yet one of the cosmos' most embarrassing mysteries isn't about something exotic, but something we should know intimately: ordinary matter. You'd think the atoms making up stars, planets, and even our bodies would be easy to account for, but when cosmologists tally up the universe's baryonic matter, the protons, neutrons, and electrons that form everything we can see, half of it is simply missing. This is the missing baryon problem, a cosmic detective story where the clues are written in empty space. For decades, scientists assumed this lost matter must be hiding in plain sight, too diffused to glow like stars but still lurking in the vast voids between galaxies. The breakthrough came when they turned their attention to the cosmic web, the intricate network of filaments weaving the universe's large-scale structure. These threads, made mostly of ionized gas, stretch millions of light years, connecting galaxy clusters like glittering beads on invisible strings. Simulations had long predicted these filaments should contain the universe's missing baryons, heated to temperatures so extreme they emit not visible light but faint X-rays. Spotting them, however, required instruments sensitive enough to tease this whisper-thin signal from the noise of the cosmos. Enter modern X-ray observatories like ESA's XMM Newton and NASA Chandra. By stacking data from thousands of filaments, astronomers finally caught glimpses of the elusive matter, not as discrete clouds but as a pervasive, ultra-hot fog. The gas in these filaments is so sparse, a cubic meter might hold just a single atom, yet its sheer volume adds up to the missing half of all normal matter in the universe. Even more astonishing, this gas isn't just sitting idle. Turbulent motions and shocks from galaxy collisions send ripples through it, a dynamic dance of particles too energetic to form stars but too tenuous to detect easily. Yet the puzzle isn't fully solved. While we've now accounted for most of the missing baryons, their exact distribution and temperature profiles still don't match predictions perfectly. Some filaments appear hotter than expected, suggesting energy inputs from hidden sources, perhaps supermassive black holes pumping power into the cosmic web, or dark matter interactions we don't yet understand. Future missions like Athena, set to launch in the 2030s, aim to map this gas in unprecedented detail, turning what was once an invisible scaffold into a high-resolution chart. What makes this search so crucial isn't just balancing the cosmic books, it's about understanding the universe's skeletal framework. These filaments aren't just passive highways, they funnel gas into galaxies, fueling star birth and shaping cosmic evolution. The missing baryons, it turns out, were never truly lost, just masterfully concealed, waiting for us to develop the tools to see the universe not as a collection of bright objects, but as a vast, interconnected system where even the emptiest spaces hum with hidden activity. When a star goes supernova, it's usually a farewell performance, a cataclysmic explosion that obliterates the star, leaving behind either a dense neutron star or a black hole. But sometimes the universe likes to break its own rules. Enter the zombie star, a stellar oddity that somehow survives its own death throes, rising from the ashes like a cosmic phoenix. The poster child for this phenomenon is SN 2012Z, a supernova that defied expectations by leaving its progenitor star still flickering in the aftermath. This particular breed of stellar explosion, classified as a Type IX supernova, is the universe's version of a failed detonation. Unlike their more violent cousins, Type Ia supernova, which occur when a white dwarf siphons too much mass from a companion and detonates completely, Type IX events seem to fizzle partway through. Imagine lighting a firework that only half explodes, leaving a charred but intact shell behind. That's essentially what happens here. The white dwarf gets blasted apart with just enough force to produce a brilliant flash visible across galaxies, yet somehow retains enough of its structure to keep shining. The survival mechanism behind these zombie stars remains hotly debated. One theory suggests the explosion might be asymmetrical, like a balloon bursting with one side ripping open while the other remains intact. Alternatively, the white dwarf could be partially disrupted, with its dense core stubbornly holding together even as its outer layers are violently ejected. Observations of SN 2012Z support this. Hubble images taken years after the supernova revealed a lingering object at the site, likely the wounded but still kicking remnant of the original star. What makes these events so fascinating isn't just their defiance of stellar death, but what they reveal about the fine line between destruction and survival. Typical supernovae are cosmic reset buttons, scattering heavy elements across space to seed new generations of stars and planets. Zombie stars, by contrast, hint at a messier, more nuanced process, one where stars can straddle the boundary between existence and oblivion. Their faint, lingering glow offers astronomers a rare chance to study the physics of almost explosions, providing clues about how matter behaves under extreme conditions that simulations struggle to replicate. While zombie stars are rare, accounting for perhaps 1 in every 3 Type Ia supernova, they challenge our assumptions about how stars die. If a white dwarf can endure a supernova, what other stellar phenomena might we be misjudging? And could there be even stranger survivors lurking in the cosmic shadows, waiting to append our textbooks once more? The universe, it seems, has a habit of resurrecting its dead in ways we're only beginning to comprehend. Somewhere in the cosmic void, a supermassive black hole is on the lam, hurtling through intergalactic space at unimaginable speeds, leaving its home galaxy behind like a discarded shell. Hubble caught this celestial fugitive red-handed in 2017. A black hole weighing millions of suns, streaking across the universe at over 4 million miles per hour, its path marked by a trail of newborn stars glowing blue against the darkness. This wasn't just a wandering giant, it was evidence of one of the most violent events imaginable, a black hole flung from its throne by the universe's own gravitational forces. The leading theory behind this cosmic ejection is as dramatic as the event itself. When 2 galaxies merge, their central black holes eventually spiral together, locked in a gravitational dance that ends in a cataclysmic collision. But according to Einstein's equations, these mergers don't just produce gravitational waves. They can also deliver a tremendous kick. If the final merger isn't perfectly symmetrical, the emitted gravitational waves carry momentum in one preferred direction, recoiling like a cosmic rifle blast. The newborn black hole gets shot out of its galaxy at speeds that defy comprehension, a bullet forged from spacetime itself. What makes this runaway black hole so mesmerizing isn't just its speed, it's the accidental artistry left in its wake. As the black hole plows through intergalactic gas, the shock waves compress and heat the material, triggering star formation along its path like cosmic breadcrumbs. Hubble's images reveal a stunning contrail stretching 200,000 light-years, twice the diameter of our Milky Way, each bright, not a stellar nursery ignited by the black hole's passage. It's a brutal yet beautiful paradox, an object known for devouring light becoming an unlikely midwife to new stars, yet mysteries linger. How common are these gravitational wave recoils? Could there be entire populations of rogue supermassive black holes drifting unseen between galaxies? Simulations suggest recoils powerful enough to eject black holes entirely are rare, but even partial kicks could leave some lurking in galactic halos, invisible until they interact with new material. Future gravitational wave detectors like LISA might catch these events in real time, measuring the precise moment a black hole gets catapulted into oblivion. This discovery forces us to rethink the life cycle of supermassive black holes. Far from being static anchors at galactic centers, they can be dynamic, even transient occupants shaped by violence and chance. The runaway black hole isn't just an outlier, it's a glimpse into the chaos underlying cosmic order, where even the most massive objects are subject to the universe's capricious whims. If there's one thing astronomers thought they understood, it was the slow, methodical dance of galaxy formation, a process taking billions of years, where clouds of gas gradually coalesce, fragment, and spin into the majestic spirals we see today. But the universe, it seems, loves a good plot twist. Enter the impossible galaxies, pristine, fully formed disk galaxies like our own Milky Way, caught in telescope snapshots of the early cosmos, existing so soon after the Big Bang that they shouldn't, by all known physics, be there. These cosmic rule breakers first stunned researchers when the Hubble and later the James Webb Space Telescope peered back to a time when the universe was just 5% of its current age. Instead of the expected chaotic blobs of young, merging galaxies' messy construction sites strewn with stellar debris, they found sleek, rotating disks with well-defined spiral arms, looking as polished as galaxies 10 billion years their senior. One standout, the galaxy Ulma J0, 81740, 86 plus 135,138, 2, flaunted a mature disk structure a mere 1.5 billion years after the Big Bang. That's like finding a fully built skyscraper in the middle of a primordial swamp. The problem, our best simulations of galaxy evolution can't produce such orderly systems that quickly. Gravity works slowly, and turbulence from early star formation should have kept gas too agitated to settle into neat disks so soon. Yet these galaxies didn't just form, they thrived, with stellar populations so ancient they imply stars began assembling at cosmic dawn itself. Some theorists now suggest that the early universe's dark matter halos might have been unusually smooth, providing calm nurseries where gas could cool and spin undisturbed. Others propose that super-efficient star formation, fueled by pristine hydrogen free of heavy elements, allowed disks to stabilize far faster than modern galaxies. But the most tantalizing possibility is that we're missing a fundamental piece of physics. Could dark matter interact with itself in ways that accelerate structure formation? Or did the first black holes seeding galaxies earlier than we thought act as gravitational anchors, hastening order amid the chaos? Every new observation of these primordial disks chips away at our assumptions, forcing us to rewrite the story of cosmic dawn. The impossible galaxies aren't just outliers, they're signposts pointing to chapters of universal history we've barely begun to read. What makes these discoveries so exhilarating is their defiance of cosmic patience. The universe, we assumed, took its time to build complexity, but these galaxies whisper a different tale, one where elegance can emerge from the storm far sooner than we dreamed. As telescopes probe even deeper into the past, who knows what other impossibilities might be waiting, ready to reshape our understanding of how everything came to be. Most galaxies wear their structure like a badge of honor, bold spiral arms thick with stars and gas swirling in luminous splendor. But the phantom galaxy M74 plays a different game. At first glance, this face-on spiral in Pisces seems almost spectral, its delicate arms so faint they vanish in many telescope images, earning it its haunting nickname. Yet when astronomers peer through special filters capturing ultraviolet and infrared light, the phantom transforms. Its wispy arms come alive, glowing with newborn stars and intricate filaments of dust, tracing a pattern so pristine it's considered the archetype of a grand design spiral. The contradiction is mesmerizing, a galaxy so ghostly in visible light, yet so intricate when viewed through the universe's hidden lenses. What makes M74 truly fascinating isn't just its elusive beauty, it's the invisible scaffolding holding it together. The Phantom's arms are too faint, too tenuous to maintain their structure through gravity alone. Like ink dropped into water, they should have diffused into chaos eons ago. Yet here they are, clinging to their spiral perfection. The secret, a vast halo of dark matter, its gravitational embrace quietly shaping the galaxy's form. While we can't see this invisible skeleton directly, its influence is written in the orbits of stars and gas clouds, moving faster at the galaxy's edges than visible matter can explain. The Phantom's elegance, it turns out, is a dance choreographed by the unseen. The interplay between light and shadow in M74 offers a rare window into dark matter's role in galactic design. Unlike some galaxies where dark matter clusters centrally, here it seems distributed in a way that amplifies the spiral pattern, like an artist using faint pencil lines to guide a watercolor. This delicate balance challenges assumptions about how dark matter interacts with ordinary matter, suggesting it might not always clump in predictable ways, but instead flow into subtle, large-scale patterns that sculpt galaxies from the shadows. But the Phantom has another trick up its sleeve. Its eerie transparency makes it a perfect laboratory for studying stellar life cycles. Unlike denser galaxies where dust clouds obscure the view, M74's sparse arms let astronomers peer straight into its star-forming regions, watching stellar nurseries ignite and fade with rare clarity. The galaxy's very faintness, once a hurdle, becomes a gift, a cosmic X-ray revealing the bones of galactic evolution. In the end, the Phantom Galaxy is more than just a pretty enigma. It's a reminder that the universe's most profound stories are often told in whispers, not shouts. From the dark matter we can't see to the delicate spiral arms we almost missed, M74 challenges us to look deeper, to question not just what's visible, but what lies hidden in the spaces between. Some of the universe's most baffling structures aren't sleek galaxies or swirling nebulae, they're colossal, amorphous clouds glowing with a ghostly hue, drifting through the cosmos like cosmic jellyfish. Meet Lyman alpha blobs, enormous hydrogen gas clouds so vast they could swallow entire galaxies, and yet they remain one of the deepest mysteries of the early universe. These gigantic blobs, some stretching hundreds of thousands of light years across, emit a specific wavelength of ultraviolet light known as Lyman alpha radiation, painting the darkness with an eerie, diffuse glow. But here's the twist, no one knows exactly what's powering them. Discovered in the late 1990s, these blobs defy conventional explanations. Normally, gas clouds light up when bombarded by energy, whether from newborn stars feeding black holes or collisions between galaxies. Yet many Lyman alpha blobs float in near solitude, untethered to any obvious energy source. It's like stumbling upon a neon sign in the middle of a desert, powered by no visible electricity. One of the largest, Lab 1, spans 300,000 light-years and shines with the brightness of billions of suns, but its core shows no signs of the frenzied star formation or quasar activity that should accompany such a radiant spectacle. Theories about their origins range from the dramatic to the downright exotic. Some suggest these blobs are cosmic lighthouses, illuminated by the intense radiation of hidden galaxies or supermassive black holes buried deep within their folds. Others propose they're the aftermath of primordial gas raining down from the cosmic web, cooling and glowing as it condenses into the universe's largest reservoirs of raw material. There's even the tantalizing possibility that dark matter, whose gravitational pull shapes the universe on the largest scales, might be indirectly heating the gas through particle interactions we've yet to detect. What makes Lyman alpha blobs so captivating isn't just their mystery, but their role as cosmic time capsules. They're relics of an era when the universe was far denser and more chaotic, and their sheer size suggests they played a crucial part in galaxy formation, acting as nurseries or fueling stations for the first generations of stars. The James Webb Space Telescope is now peering into these enigmatic structures with unprecedented clarity, searching for the faint fingerprints of young stars or hidden black holes that might solve the puzzle. Until then, these glowing giants stand as humbling reminders. Even in the infancy of the cosmos, the universe was already crafting wonders we're only beginning to comprehend. Among the countless oddities of quantum physics, none stretch the imagination quite like the concept of unparticles, a form of matter so bizarre it defies the very categories we use to describe reality. Picture something that isn't quite a particle, not exactly a wave, but instead occupies a ghostly middle ground, behaving in ways that make even seasoned physicists pause. This isn't just theoretical curiosity, it's a radical reimagining of the universe's building blocks, one that could rewrite the rules of everything from black holes to the Big Bang. The idea of unparticles emerged in 2007, when physicist Howard Georgi proposed that certain high-energy interactions might produce matter with scaling symmetry, a property where the substance has no fixed mass or size, but instead behaves like a fractal, displaying self-similarity at any scale. Unlike electrons or quarks, which have definite properties, unparticles would blur the line between particles and energy, acting more like a continuous field with particle-like tendencies. Imagine dropping a stone into a pond and watching the ripples, but instead of distinct waves, the water responds with a single, unbroken disturbance that somehow contains hints of individual droplets. That's the eerie essence of unparticle behavior. Why does this matter? Because unparticles could be lurking in the shadows of known physics, subtly influencing phenomena we've struggled to explain. Take dark matter, for instance. If unparticles exist, they might interact so weakly with ordinary matter yet exert gravitational pull that they've been hiding in plain sight all along. Or consider neutron stars, where matter is crushed to unimaginable densities. Under such extremes, unparticle effects could alter how neutrons behave, producing exotic states of matter we've never observed. Even the early universe might hold clues. Unparticle fields could have shaped the rate of cosmic expansion, leaving fingerprints in the cosmic microwave background that we've yet to decode. The wildest implication, unparticles might hint at a deeper layer of reality, where the distinction between particles and forces dissolves entirely. In quantum field theory, particles are excitations in their respective fields, but unparticles suggest these excitations don't have to behave like discrete billiard balls. They could be smeared across spacetime, neither fully localized nor entirely diffuse. Some theorists speculate that unparticle-like behavior might emerge in high-energy experiments like the Large Hadron Collider, where collisions could temporarily liberate unparticle degrees of freedom from the fabric of spacetime itself. Yet for all their promise, unparticles remain a tantalizing what-if. No direct evidence has confirmed their existence, and skeptics argue they're a mathematical curiosity with no physical counterpart. But that's the beauty of theoretical physics. It dares to explore the impossible, pushing the boundaries of what the cosmos might allow. Whether unparticles are real or not, they remind us that the universe is under no obligation to conform to our expectations. Sometimes the most profound discoveries begin with a simple, heretical thought. What if reality doesn't play by the rules we've given it? At the heart of modern cosmology lies a deceptively simple question: how fast is the universe expanding? The answer should be straightforward: measure some distances, track some redshifts, plug in the numbers. Yet when astronomers compare results from two of our most trusted cosmic yardsticks, they get wildly different answers. This growing rift, known as the Hubble tension, isn't just a minor discrepancy, it's a full-blown crisis threatening to upend our understanding of cosmic evolution. On one side, we have meticulous measurements of the cosmic microwave background, the afterglow of the Big Bang, suggesting an expansion rate of about 67 kilometers per second per megaparsec. On the other, observations of pulsating stars and exploding supernova in the nearby universe insist the rate is closer to 73. That 6-kilometer gap might sound trivial, but in the precise world of cosmology, it's a chasm, one that grows more stubborn with every new dataset. The stakes couldn't be higher. If both methods are accurate, something fundamental in our cosmic playbook is missing. Imagine two clocks, one atomic, one mechanical, ticking in perfect sync for decades until suddenly, inexplicably, one starts running faster. The discrepancy would imply hidden forces at work. In cosmology's case, the tension could point to exotic new physics, perhaps an unknown form of dark energy that briefly surged during the universe's adolescence, or a fifth force tweaking gravity on the largest scales. Some theorists speculate about early dark energy, a fleeting field that altered the expansion rate in the universe's first few 100,000 years, leaving traces too subtle for current instruments to detect directly. Others wonder if dark matter isn't as cold as we've assumed, with particles just energetic enough to nudge galaxies apart faster than expected. Yet before we rewrite the textbooks, there's the nagging possibility of mundane errors. Could supernova, our standard candles for measuring cosmic distances, be less reliable than we thought? Recent studies suggest some supernova might evolve differently in varied galactic environments, subtly skewing results. Alternatively, the cosmic microwave background measurements might be missing systematic biases, like misjudging how much interstellar dust scatters its ancient light. Even the megaparsec itself, the unit defining cosmic distances, could be miscalibrated due to quirks in how we chain together different measurement techniques. It's a detective story where every clue seems to contradict the next. What makes the Hubble tension so electrifying is its refusal to yield. Unlike past cosmological puzzles resolved by better data or tweaked models, this one digs in deeper with each observation. The James Webb Space Telescope's razor-sharp infrared vision was supposed to settle the debate, but its first results only sharpened the divide. Meanwhile, emerging techniques like gravitational wave astronomy offer entirely new ways to measure expansion, adding fresh voices to the argument. Some researchers now openly speculate that we're witnessing the cracks in our cosmic framework, the first hints of a paradigm shift as profound as the discovery of dark energy itself. Whether the solution lies in revolutionary physics or humbler measurement fixes, one thing's certain: the Hubble tension is more than a technical glitch, it's a cosmic provocation. Every failed reconciliation, every stubborn data point forces us to question assumptions we've held for decades. In that tension, there's beauty, the universe reminding us that its deepest truths are never handed over easily, but earned through relentless curiosity and the courage to confront the unknown. From the Great Attractor's relentless pull to the eerie whispers of fast radio bursts, from the phantom chill of the Eridanus supervoid to the cosmic defiance of zombie stars, we've journeyed through 30 of the universe's most baffling enigmas. Each one isn't just a curiosity, it's a crack in the facade of our understanding, a challenge hurled at the feet of science, daring us to look deeper. These mysteries aren't roadblocks, they're invitations. Every unexplained signal, every anomalous galaxy, every runaway black hole is a thread in the grand tapestry of discovery, pulling us toward answers we haven't even learned to question yet. Think about what these phenomena reveal. The universe is messier, wilder, and more imaginative than our textbooks could ever capture. Dark flow hints at forces beyond our cosmic horizon. The Hubble tension exposes gaps in our foundational physics. Lyman alpha blobs glow with the secrets of the primordial cosmos. Even the humblest anomalies like the Kuiper Cliff's stark boundary or Tabby's star's erratic flickers remind us that the familiar can hide profound unknowns. Science doesn't march forward in straight lines. It stumbles, recalibrates, and leaps when faced with the inexplicable. So here's the real magic. These puzzles belong to you as much as they do to astronomers. Every time you look up at the night sky, you're part of the conversation. Maybe you'll spot a new fast radio burst pattern in a public dataset, or have a wild theory about the axis of evil's alignment. The universe isn't just for experts, it's for the curious. Before you go, tell us in the comments which mystery left you spellbound. Was it the diamond planet's glittering allure or the cosmic horror of the Great Filter? Hit subscribe to join us as we unravel more cosmic riddles, because the next breakthrough might come from a telescope or from you. The universe has 30 mysteries today. Tomorrow, who knows, but the search is what makes it exhilarating. Keep wondering, keep questioning, and remember, the best discoveries start with a simple, thrilling thought.